Number of interstitial atoms in a solid, exact analysis. Consider the physical situation described in the previous problem. To do the problem exactly, try to find the probability P of n that precisely n interstitial positions are occupied by atoms. There are then, of course, also n normal positions unoccupied by atoms. What is the probability of encountering a given situation where n interstitial atoms are distributed in one particular way and n empty normal positions are distributed in one particular way? So we know that the interstitial position 1, 2, 3, all the way up to n will be occupied. And we're now asking the empty position being associated with the first interstitial position, first empty position, second empty position associated with this, third empty position associated with this, etc. for the nth empty position associated with the nth interstitial field position. So for one atom, we have probability of being in the normal position c times e to the minus beta ea, and probability of being in the interstitial position c times e to the minus beta eb. And now so that's for the first atom. Second atom, now I'm going to place it in the second position. Probability of being in the normal position is the same. So let's say we're not doing second atom, but we're doing jointly two atoms. So I'm placing two atoms in positions 1 and 2. Now the probability for two atoms will be c square e to the minus beta ea square, and probability of being in both of them being in the normal position, the interstitial position, will be c square e to the minus 2 beta eb, etc. And for n atoms to be jointly occupying these n positions, the probability A of n will be c to the n e to the minus beta n ea, and probability of not occupying, or probability of having the interstitial position, we will have c to the n e to the minus n beta eb. So we will find that probability of occupying n interstitial positions, one particular distribution of n interstitial positions divided by a probability of occupying one particular distribution of n normal positions jointly by n atoms. So it's jointly because we're multiplying probabilities. This will be e to the minus beta n eb minus ea. So the ratio of the probabilities pb to pa for n atoms will be e to the minus beta n epsilon. Because remember that in problem 4.24 we said eb minus ea is epsilon. So this is problem 4.24 statement. So we're continuing the same problem, doing exact analysis. Okay, so look at part B. In how many ways is it possible to distribute n atoms over n possible interstitial positions? In how many ways is it possible to distribute n missing atoms over n normal positions? Well, we know the answer for this one. Number of distinct ways of choosing n objects out of capital N objects is given by combinations of capital N objects taken n at a time, that is n factorial, capital N minus n factorial, n factorial. So that is the number of different distinct ways I can do this, and it's the same for whether I'm distributing n atoms over n possible interstitial positions, or I'm distributing n missing atoms over n capital N normal positions, the same result. Okay, so same for both questions. Part C. Combining the results of parts A and B show that the probability of having precisely n interstitial positions occupied is given by this expression. Now, how many different ways of having capital n out of capital N interstitial positions and n out of capital N normal positions? So we have to combine these two. So I already know that the probability of having n atoms in one particular way is e to the minus beta n epsilon in position B. So this is for one particular way. Now, that was in part A. In how many different ways can I place n atoms in capital N interstitial positions and missing atoms in capital N normal positions at the same time, so jointly. So I'm trying to do this at the same time, which means I will be multiplying the number of configurations. So I will find that the answer to this question is combination of capital N objects taken n at a time multiplied by a combination of n objects taken n at a time. One is for placing n atoms in capital N interstitial positions, the other one for placing n missing atoms in capital N normal positions. So this will be n factorial and capital N minus n factorial square. So the probability of having n interstitial atoms is proportional to the number of different ways I can do this with the same energy. So this will be n factorial divided by capital N minus n factorial square e to the minus beta n epsilon. So what is this? Corresponding to the same scenario, I have this degeneracy, right? So there are so many different ways I can do it, and I will still have the same energy, n times epsilon, for this configuration. So this will be the answer. Now in part D, the probability P of n has a sharp maximum for some value n tilde. To find this value, consider a natural logarithm of P of n and satisfy the condition the derivative with respect to n is 0. Since all factorials are large, Stirling's approximation is applicable. Show thus that for n tilde much less than capital N, one obtains the result that we have obtained with the approximate analysis in the previous problem. Okay, so Stirling's approximation. Remember Stirling's approximation. Natural logarithm of n factorial is n natural logarithm of n minus n. This is Stirling approximation. We have shown this in a mathematical note. Now, if I take the natural logarithm of the probability distribution of n. So basically I can see that I can write this probability distribution as a constant c times capital N factorial over capital N minus n factorial square e to the minus beta n epsilon. Now I'm taking its natural logarithm, so I get natural logarithm of the constant c. Then I will have natural logarithm of exponential, which will give me a minus beta n epsilon. And then I have natural logarithm of the square, which will give me a factor of 2. And then I have natural logarithm of capital N factorial minus natural logarithm of n factorial minus natural logarithm of capital N minus n factorial. So this will give me, if I apply the Stirling approximation, natural logarithm c minus beta n epsilon plus 2 Stirling approximation for ln natural logarithm capital N factorial is capital N natural logarithm n minus n, and the Stirling approximation for natural logarithm of n factorial is now going to be with the minus sign, minus n natural logarithm n. The minus will become a plus, so it will be plus n. And then Stirling approximation used for capital N minus n factorial. This will be minus capital N minus n natural logarithm capital N minus n because of the minus sign up front. And the minus sign in the Stirling approximation will become a plus. So I will have plus capital N minus n. So you can see that I have some cancellations here. So there is one cancellation, this minus capital N will get rid of this plus capital N. And there's another cancellation for n here. So this n will get rid of this n. So I will be left with natural logarithm of c minus beta n epsilon plus 2 capital N natural logarithm of n, capital N, minus n natural logarithm of n. And then I have minus capital N natural logarithm of capital N minus n. And then I will have plus n natural logarithm of capital N minus n. Now I'm ready to take the derivative. Take the derivative, partial derivative with respect to n, and equate it to 0 to find the most probable value. The first one is a constant, so that will give me no contribution. Second term will give me a minus beta epsilon. And then I have plus 2 times, let's see here, capital N, natural logarithm capital N, no contribution, minus n natural logarithm n will give me a contribution. The first term will be minus natural logarithm n, second term will be minus n divided by n, derivative of natural logarithm of n with respect to n. And then I will have minus capital N, derivative with respect to n of inside is minus 1 divided by capital N minus n, that's the derivative of natural logarithm. And then the first term in the n natural logarithm capital N minus n will be natural logarithm capital N minus n. The second term will be n times derivative with respect to n of inside is minus 1 divided by capital N minus n. So if I simplify this a little bit more, the derivative of natural logarithm of the probability with respect to n is the first term minus beta epsilon plus 2 now I have minus natural logarithm of n. Uh, Here I have a minus 1. So there is a minus 1 here. Then I have minus minus plus capital N over capital N minus n plus natural logarithm capital N minus n, and then I have minus n over capital N minus n. You can see that this is going to become del ln p del n is equal to minus beta epsilon plus 2. Now I have plus capital N and minus n, so this is going to give me a 1 minus ln n minus 1, so plus capital N minus n over capital N minus n plus ln capital N minus n. So this is plus 1 and minus 1 will cancel. So I will be obtaining as a result minus beta epsilon plus 2 ln capital N minus n divided by n. This is going to equal to 0, so we're going to find the most probable value n tilde here. So we will see that n tilde capital N minus n over n is equal to beta epsilon exponential beta epsilon over 2, or I can write this as n evaluated at n tilde divided by capital N minus n tilde is e to the minus beta epsilon over 2, and since n tilde is much less than capital N, I can neglect this term. So this is going to give me n tilde divided by capital N is approximately e to the minus beta epsilon over 2, which is indeed the answer that is suggested in the problem statement expression I. Okay, so now we're doing an exact analysis for the interstitial atoms in a solid. First, we looked at the probability of having one particular configuration, one particular way of occupying n interstitial positions, leaving behind a particular way of n empty spaces. So for one atom, the probability of occupancy of one possible interstitial position is proportional to e to the minus beta EB. And for two atoms to jointly occupy two positions, it's the square of this. For n atoms, it's to the power n. So the probability of having n atoms occupying n particular interstitial positions divided by probability of having n missing atoms having n particular positions, normal positions, we have the ratio e to the minus beta n epsilon. The number of distinct ways of choosing, so now we're not talking about one particular configuration. We're asking in how many ways is it possible to have n out of capital N interstitial positions and n out of capital N normal positions, and they are both combinations of capital N objects taken at a time. And since the probability of one particular configuration was e to the minus beta n epsilon, the joint occurrence of capital N normal position, n out of capital N normal positions, empty positions, and n out of capital N interstitial filled positions is the square of the combinations. And then the probability will be the number of different ways we can do this multiplied by the exponential minus beta n epsilon. That is our degeneracy basically, corresponding to the same energy. And this gives us the probability. When we take the natural logarithm of the probability and take its derivative with respect to n, set it equal to 0, we find the most probable n value, the most probable number of atoms in interstitial positions. And we see that using Stirling's approximation, the most probable value of n is capital N multiplied by e to the minus beta epsilon over 2.